Okay, fine. So, hello everyone. So, I'm very pleased to share this the defense of Corentin Dancette about shortcut learning in visual question answering. So, we have a jury composed of two reviewers, Elisa Fromont from Université de Rennes 1, Christian Wolf from Naval Labs Europe, and then we have three examiners, Damien Tenet from Diap, Marcus Horvath from Technician University at Darmstadt, and myself at Sorbonne University, and we have Mathieu Corr, the supervisor of the PhD. So, Corentin, you have 45 minutes to present your work, and then we switch to the question session.
Thank you, Nicolas. So yeah, I will present my work on shortcut learning in visual question answering, which I did during my PhD. So first, deep learning, most of you know, it has been extremely successful at a lot of different tasks involving image and text modality. For example, object detection, image classification, image segmentation for the image modality, and then for the textual modality, machine translation or summarization. And there are many other examples where deep learning has been extremely successful. And I'm going to look a bit more about those two specific modalities, image and text. So for image, the most successful and common architecture is the convolutional neural network, or CNN, which is composed of a series of convolutional networks, convolutional layers, which are learned on some data set. And one of the most common data set is the ImageNet benchmark, which has around 1 million training images over 1,000 classes. And deep learning is the most successful approach on this benchmark in the past few years. And we have also a different kind of tasks, so different from classification, for example, captioning, which is describing an image, object positions, or segmenting an image, with, for example, Microsoft Photo dataset. And for the textual modality, I'm showing here one specific task, which is question answering. And this is the task of answering a question about some piece of context here. So, like, for example, what is the capital of Germany? And it's Berlin. It's based on the context, so it requires no outside knowledge. And this is from the SPOT dataset from 2016. And in text, similarly to vision, deep learning has been really successful. And the most common architecture today is the transformer architecture, which is based on multiple attention mechanisms, and it's from 2017. And so we see that we have image task and text task. Now we are interested in understanding how we could combine those two modalities into a single task. And this is the main focus of my PhD, specifically visual question answering. And so visual question answering is the task of answering a question about an image. So we can take this image, for example, and ask what color are her eyes. So this is pretty simple. It's black or maybe brown. But we can also ask, what is the mustache made of? So for us, it might be simple, but for a machine, it's a bit surprising. So those questions might be complex, and they require multimodal understanding. So not only analyzing the image and the text, but how to merge those two information and come with an answer. And the VQA dataset it was released in 2015, and we have many other datasets that were released in the past few years, such as Clever, which is a synthetic dataset, or other like TaliQA, which is only focused on counting, and all have some specificities. And the applications of VQA are multiple. The most common and simple is assisting visually impaired users. So there is a dataset called VisWiz, which was released in 2018, and where the blind people were asked to take pictures and answer and ask questions about them that would be useful for them. So it's a very different data set compared to the previous one, VQA. It's much more difficult because the images might be sometimes very blurry or complex. But it's eventually an end goal for this task. And we can also think of automatic interactive systems. So you all know ChatGPT now. We can think of multimodal like ChatGPT, where we have an image and a discussion between the user and a robot, So here, what is in this picture? It's a bowl of soup with a monster face on it, and then more questions iterating on this with the history. So a typical VQA architecture is composed of three parts. So the image is encoded using a dedicated network, so usually a convolutional neural network. The question is also encoded using a question encoder, usually a recurrent neural network or a transformer. And both of these modules give us some vector representation of the image and the text. And then we can merge those two vector representations using a multimodal model, which can be of different types. You can use some bilinear fusions, attentions, transformers, and I will give a bit more details about this. And usually this task is considered as a classification task. So we have to select one answer in a set of 3,000 possible answers. And this is simpler for evaluation. But we could also think of generating long answers of not just one word. And yeah, but this is a bit harder to evaluate. I'm going to present a few VQA architectures. So for example, Mutan uses GRU, which is a recurrent neural network for the text encoding, and a ResNet, which is a convolutional neural network for the image encoding, and then uses a bilinear fusion to merge the two vector representations, and then output a classification output. Yeah, we also have architectures which use, instead of using classical convolutional neural network for the image, some use object detection models. So they first detect the objects in the image and then use those object representations to give them to the multimodal model. And this is easier usually for VQA models because questions are about objects. So you use a GRU for the text, and you use attention-based fusion. So it's like a weighted sum of all the image features, depending on the question, to then classify the correct answer. And then, so the two previous architectures were specific for VQA, and we have recently architectures like Dilbert, which are multitask and general architectures for vision and language tasks, but can be fine-tuned or can be used for VQA. And so here, this architecture also uses an object-based representation with a faster RCNN, so an object detection model. But then uses transformer layers. So here we have multiple transformer layers for the text encoding. And then we have like cross-attention transformer layers to merge the image into the text representations and the text into the image representations. And then again, transformer layer. And this is trained on a very large task agnostic vision and language data, like some captioning data, so images and captions. And then fine-tune on VQA. So it can be, but can be applied to many other tasks. And visual question answering has been so models have been really successful at VQA in the past 3 years. You can see that the most recent model now beat the human level at this task. And we can see two trends here that I would like to highlight. First is the number of parameters. So it has been only growing since the release of the data set from a few 100 million to now more than 1 billion parameters. And also the kind of architectures we had. So in the beginning, we had architecture dedicated for VQA and use bilinear fusion or the various architectures. But recently, we have only pre-trained transformers on a very large image and text data. And so we can wonder, are those models really solving the VQA task? Are they actually really better than humans? And this, we introduce the next problematic, which is shortcut learning. The shortcut learning, the idea is that the data sets usually have some biases or some superficial correlation that will be learned by models to output an answer that might be correct, but that is not a causal feature. And in the image modality, a simple example would be to recognize pneumonia. And if we have images from multiple hospitals, which have different distributions of pneumonia versus not pneumonia, and then the model might use to recognize the hospital instead of recognizing if there is a pneumonia. And this will help him classify, but this is not what we want the model to do. And in the text, we can think of question answering again. And a lot of models have very superficial correlation with the last sentence of the text, and we can fool them by adding some useless information in the last sentence, and they get the wrong answer. And so in VQA, more specifically, we know that they are usually too reliant on the question. So here is an example that analyzes this, and they show that if you ask how many zebras, the model usually answers 2 without really looking at the image. There is 1 here, 4 here, and 3 here, and gets wrong and says 2 because 2 is the most common answer when you ask how many in general and for zebras in particular. And so some solutions have been proposed for this. Some work proposed to balance the training data sets. So for a given question, they make sure that they have similar images that have different answers. So here, who is wearing glasses? We have a man here and a woman here. And this makes model a bit less reliant on textual shortcuts only, but they have to look at the image to be able to answer the question. And we can also think of some evaluation benchmarks, which have a distribution shift between the training and the testing set. So here, we have what sport. On the training set, the most likely answer is tennis, and on the testing set, it is baseball. And so if a model only learns some textual correlations, it will be wrong on the testing set. And so here are the chapters of this presentation. First, I'm going to talk about reducing shortcut learning, then how to detect multimodal shortcuts, and finally, how to improve reliability of VQA models in their distribution shift. So first, I'm going to look at reducing shortcut learning. So as I said before, VQA models, they tend to be biased toward the question modality. If we ask a simple question like, what is the color of the banana? And we give a yellow banana here, the VQA model will certainly get it correct. But if we ask the same question with a green banana, then the model might be incorrect because it didn't see a lot of yellow bananas during training. Only, it only saw yellow bananas, and it will still say yellow. And this is the problem we want to address here. And so there are multiple inductive biases that impact the model learning, the architecture, the loss function, the training data, the optimization procedure. And here we will look at the first two, architecture and loss function, and more specifically, the loss function. And this section is based on 2 works, one at NUIPS and one at a VQA workshop at CVPR. And so, just as a reminder, the VQA architecture classical, we have 1 vision encoder, 1 question encoder, and 1 multimodal VQA model. And we want to reduce this kind of link here, which the VQA model uses too much the question information, and not enough the image information. And we propose a strategy we call the REBI for reducing unimodal biases. And here the idea is that we'll add a secondary branch here, which will predict the answer only using the question. So it's a completely biased model. It doesn't use the image, so it will always say the banana is yellow because it cannot access the image information. And then to train the main VQA model, we will mask its predictions with the predictions of the question-only model. So this, we train both as a kind of ensemble of the 2 models. And this will, so this way, the question-only branch will learn the superficial correlations, and the VQA model can learn the rest. And I'm going to explain a bit more how this works. So on an example here, again, the yellow banana, the VQA model, which we say yellow with a high probability here, 95%, and get a small loss here because it's very close to the correct answer. And here, if we merge the 2 predictions from the regular model and the question-only model, the question-only model will also say it's yellow because it's biased towards the question, and this will increase the score of the correct answer. And so the loss will decrease, will be very low. And then we will have, we won't have a lot of learning on this example. The model won't learn a lot from this example because it's very small loss. On the contrary, if we have a more difficult example, so a green banana, which is very rare in the training set, the model will be a bit confused. Maybe it will say a half probability of green and half of yellow. But the correct answer obviously is green. And when we merge with the question only mask, this mask here will still say it's yellow because it doesn't see the image. And so this will increase then the probability of the wrong answer here. And this will make the loss go higher than the regular loss. And there will be more learning on this example compared to the previous one. And so to summarize, we leverage the capacity of the question-only model to capture the biases, and we encourage the model to learn from rare examples, and we discourage it to learn from common and easy examples. So a few results here. Those are on the VQA-CP V2 data set. So I showed it before. It's where the training set and the testing sets have different distributions, and it's made it's a different distribution condition on the question. So if you rely too much on the question, the model will have a very low score. And you can see a question-only model here has only 15% accuracy on the whole data set. And compared to our baseline architecture, which is the regular VQA model, which has 38%. Here we see that our method has 47% accuracy. And we can look at the different answer types. So if we look at only yes/no questions, we also are much better on the baseline and also on the number of questions as well. So this is the how many type of question. And compared to the previous state-of-the-art model, which has an adversarial loss on a base VQA model, our method also performs much better. So a few qualitative examples here. So first here, if we look at only the questions that start with what color and has the word banana in it, on the training set, we have mostly the yellow answer. And this is the testing set where we have mostly green answer on the right. And what we see for the baseline VQA model will be a bit confused, as I say, and we answer for half of the question green and for half of the question yellow, about half. And with the method Ruby, it's much better, and you can see that the model answers most of the questions correctly and still gets a small proportion wrong. And we can also look at the attention maps of the model. So this is a model that is has an attention mechanism. So we can look at which region in the image it focuses to output the answer. And for example, here on the second line, we ask what color is the top part of the fire hydrant. And the baseline, which is not trained with the Ruby, looks at the whole fire hydrant and says yellow. And with our Ruby method, it focuses only on the top part and has the correct answer blue. So a side effect of Ruby is that it might help the grounding and the prediction to, and helps the model to look at the correct region in the image. And a similar example here, notice the color of the star on the fire hydrant. We see that with Ruby it focuses on the star and not on the rest of the hydrant. And we have I have a following work which is related to this one, where we look only at the counting questions, so questions that start with how many. And we explore another strategy, which is architectural priors. And so we create a model which has some inductive biases in its architecture, so that the answer is grounded in the image, and that it directly selects the objects to be counted, whereas the previous models were classification models which didn't have this grounding. And this gives us more interpretability, because if we ask here how many giraffes are shown, in addition to getting the correct answer too, we can also look at the objects that were selected. So to conclude, changing the inductive biases of a model and a learning are very effective to reduce shortcut learning. So as I showed with bias function or architectural priors. And as perspective, we can explore other kinds of inductive biases. So some work have been proposing other loss functions that look at the semantic space of VQA. Or we can look at some optimization procedure which consider different subset of the data, using different subset of the training data that have different distributions, and use this to help the learning, or also modify the training data to add some maybe noise and help the model to learn the correct decision, the correct behavior. Okay. So in the next session, I'm going to talk about detecting multimodal shortcuts. So as we said previously, VK models tend to rely on shortcuts. So here is another example of simple shortcuts. If you ask a question with the word "what color in sky," the answer will be most likely blue. And previous works, they focused mostly on questions coming from shortcuts coming from the question. So would be an example. We have only textual words here, and there is no vision information. And also we can think of some problem with the previous benchmark VQACP, where we have adaptive overfitting and methods that were designed for VQACP might not work for other kind of distribution shifts, and so it's important to have new benchmarks that are better to test this. And here we propose an analysis of multimodal shortcuts. And so here by shortcuts, we mean simple decision rules that contain some textual words, so word sport, for example, and also some visual objects from the image, so a racket. And the occurrence of these words and these visual objects are associated with an answer with very high probability, so tennis here. And this seems to be a correct way to answer a question about sports. But if we can find some counterexamples, if you look at this question, what sport field is in the background, you can see that there is a soccer field behind, but and the correct answer is soccer and not tennis. But when we ask VK models, Alban and Gilbert, for example, they will both reply tennis. So they certainly learned kind of shortcut similar to this one. And so here we propose a method to find multimodal shortcuts such as this one, and an evaluation benchmark that is composed of counterexamples. And this is based in another publication at ICCB. So our goal is to detect multimodal shortcuts. So we start from a simple image and a question like this: what sport is this tennis? And then we run an object detection model on top of on the image, and this will give us some visual labels for the objects that are present in the image, so racket, ball, and man here. And we also we put them in our data set, and we also put the questions from the words from the question, and we also put the answer, and this will give us a binary data set of tokens that are in the training set. And then we can run, we can search for correlations in this data set here. And we might discover that some tokens appear very frequently together. For example, what sport, racket, and tennis is a very common subset of tokens which appears frequently together. And from this, we can deduce a decision rule. So if we have what sport and a racket, then the answer might be tennis. And we can see the metrics here. Support will be the number of times that this shortcut appears in the training set, and confidence is how many times this shortcut is correct. So here, very likely to be correct, 28%. We have multiple type of rules. So they say textual only rules. So for example, what is color snow? Give us a white with a high probability. And we have some supporting examples here and also counter examples. Here we ask the color of the snowsuit and not of the snow. We have some visual only rules, which are a bit less interested and have usually very low confidence, because the VK data set, to answer a question and to know what kind of answer you expect, you usually need some question, the question to know if you should answer a sport or yes, no, or anything. And yeah, they usually have very low confidence in support. And the ones that are really interesting to us are the multimodal rules. So I presented this one before, which have usually very high confidence and are very common in the data set. And so yeah, we can see again a supporting example and a counter example. And we can use all those counter examples to create an evaluation benchmark and so evaluate models on them. And we would think that if they learn the correct mechanism, then they might get those correctly. But if they learned the simple shortcuts, they will get those incorrectly. And this is our evaluation benchmark. And so a few here are the results. So first we evaluate some reference VQA models, so Updown and Gilbert, which I presented before. So this is the VQA accuracy in the whole testing set. They have a high accuracy of 63 and 67 here. And if we relate them on the counter example subsets, we see that there is a huge performance drop here, which suggests that they did learn some of those shortcuts. And then we can look at bias reduction methods. So all those bias reduction methods, most of them are designed for VQACP here. And so they all get a very high score on VQACP. So they are all based on Updown here. So this is the base score. And they are all much better. So at least +5 to +20 points. But here on the counter example subset, you can see that none of them really improve the score. So the best is +0.5, but very small compared to the improvement on VQACP. And some even degrade the performance, and we evaluated Ruby from the first section. And it's the same. So none of them really helps here. And this is a bit surprising, but also maybe not, because they were designed for the specific kind of distribution shift for VQACP, some of them. And this might explain why they don't work to reduce multimodal shortcuts in general. To conclude this section, VQA shortcuts are not only textual, they are also multimodal, and this is again a very common shortcut. And current bias prediction methods do not work well to mitigate those multimodal biases, as they often focus on question biases. And so we would need some new kind of bias prediction methods to tackle this problem, and to reduce vision and language shortcuts. Some idea we could have is to use those counter examples to create some new examples that, or to use those rules to create some new counter examples using image editing or image generation tools, which are now very good at creating realistic images. And we could also apply this similar strategy for other kind of multimodal tasks. So the third section of this work, it will be about improving reliability of VQA models. And this section is a bit tangential to the two previous ones. It's not directly about shortcut learning, but it is still related in a way. So I will explain a bit more what we call reliability. So the goal is to return, in addition to an answer, now we want to return a confidence score. So here we ask, what is the track? So the VQA model might get it correctly here, and it does, it says code track. And it's also a good 90% confidence. So we might trust the model on this decision and say, okay, I believe you, and so I trust this answer. But on a more difficult example, we ask what brand is this computer. And the brand is very hard to see on the image, so the model might get it right or wrong, but we don't know, but it will give a very low confidence here. And we will know that we cannot really trust the prediction here, and that we might need to abstain from answering instead of giving the answer, to not mislead the user. And so yeah, more formally, the idea is to have a function which will give, G, which is will give us either 1, which is answer, or 0, which is abstain from answering, based on some threshold on the confidence and an additional function here, G prime, which would be this number here. And this is also based on a publication at CVPR this year. And so, yeah, this is so it's a bit tangential to the shortcut problem, but it is still related when we think of evaluating out-of distribution, because if a model has learned some shortcuts, then it is very likely to be wrong on some out-of-distribution examples, but also it might be very overconfident. It will be wrong, but it will say, okay, this looks like a shortcut I learned, so I'm very confident this is the right answer. And so it's very important to have a way to measure this confidence, and especially for out-of-distribution. And in this work, we evaluate both in distribution cases and out-of-distribution cases. So this requires some other metrics to evaluate. So we cannot only look at the accuracy, because we have a second prediction, which is the confidence. And the two main metrics are coverage and risk. And the coverage is after we select a specific threshold, we say, okay, above 90% confidence, I will answer this question. Coverage would be the amount of the size of the answered subset. So how many questions did I answer and I didn't abstain? And on this subset, we might get some questions right and some questions wrong. And the risk here is the error rate on the answers on this answered subset. And so we can plot a curve here, which is the risk coverage curve. And so for a given coverage, for example, if we answer around 40% of the data set, we have an associated risk. So here around 0.02. And the more questions we answer, the higher the risk will become. And and so we can compute a global metric which doesn't depend on some specific threshold, which is the AUC, the area under this curve here. And so here the lower is better, because for a given coverage we want the minimum risk on this subset. So here are some baselines which are commonly used in this problem. The first one would be to use the probability of the model. So usually deep learning models, classification models, in addition to an answer, they return the probability of this answer. And so we can think of using this directly as confidence. Another approach would be to train another model on top of the first VQA model. So it should call a selector or a selective predictor. And it's here we consider it as a multi-layer perceptron that takes as input the internal features of the VQA model and is trained to predict the confidence of the model. So predict if this answer is right or wrong. And there have been multiple papers that try this strategy for VQA here or for other tasks as well. And so to train the selector, we need to have a two-step training process. So we first train the VQA model on a training set equal A. And then once we have this VQA model which is trained, we freeze it, so we don't update its parameters anymore. And on the new training subset B, we will take an example X from this, forward it to the VQA model, and this will give us its correctness. So we know if it's correct or incorrect. And then we can train the selector G using the features from the model F to predict this label, correct or incorrect. So a score between 0 and 1. And so this works usually very well, and I'll show some results after. But the problem is that we need to split the training data into two subsets. And this is a bit unfortunate, because deep learning models usually the more data we have, the better performance they have. And we would want to train the VQA model on the full data we have, and the selector also on the full data that we can get. especially since all this data needs to be labeled, we need the real answer here to train the selector. And so we propose a strategy to address this issue, which we call learning from the field. And so it's still a two-step process here, but a bit different. So first, we train a VQA model on the full training data. D here, which would be A plus B from the previous slide. And in addition to this VQA model, which should be stronger and should have better performance than the previous model, we train also N other models with only a partial training data. So for example, here we train 3 models, each on 2/3 of the data. And each of them has a held out subset, which is different in all the models. And this will allow us to train the selector on the full data. And so here I show how we do this. So let's say we take a D1, for example, here, which was the held out set for the model F1. And so we forward our example first in this model F1 to get the correctness. So we will know if F1 classifies it as correct or incorrect. And then we also forward it to the VQA model F, which is the strongest model. And F was trained on X. So F will certainly be correct on X because we know that deep learning models usually overfit their training set and have a very high score on all the training data. But we take the features of this model to give as input to the selector. And this is trained. And then we train the selector to predict the labels from the model F1, which didn't see X during training. And why do we do this? And why don't we just train everything on the same data without worrying about this complex method? The problem is that, as I said, the VQA model F will be overfitting on the training set and will be very good on this data D here. And if we train G, predict the correctness of F, it will get only basically correct labels and we'll learn to say everything is correct and the VQA model is very strong. And using this method, which is similar to cross-validation, we can avoid this kind of distribution shift between the selector training and the selector testing. And to evaluate this, as I said, we want to use both in-distribution data from the VQA dataset and out-of-distribution data from here we use AdVQA, which is an adversarial dataset, which is collected to be to fool the VQA models. So the questions will be very hard to answer for VQA models. We can see an example here. The question is what color will the light be when the vehicle has permission to proceed? And so the answer is green, but this question is kind of hard and a model might just say red because it sees a red light on the image. And so the images are very common, are from the same data set, but the questions are very hard. And we evaluate on multiple mixtures of in-distribution data and out-of-distribution data. And we evaluate 3 models here. The first one is ClipGIL, which is a transformer-based model, and that uses clip representation. So clip is this is like the question model and vision model separately. You have 2 encoders which are pre-trained together, but uses no vision and language pre-training for the multimodal model. And we also try a model called OFA, which is also based on the transformer architecture. It has a very large vision and language pre-training on millions of captions and images, and has around 180 million parameters. And we try an OFA large also, which has around 500 million parameters. To evaluate the effect of scale also on this problem. There should be some red lines here. We can't really see, but here I'm looking at the results, the max prob lines here to the third lines for each section. And this is the macro baseline. So it's just using the probability of the model. And we look at this metric here, coverage at 1%. So here we say that we want a risk of 1%. We only want 1% error. And so we are here, what we write is the coverage. So how many questions we answered, given that we want this risk of 1%, and we select the threshold for this 1% of error. And so we can see that the models are quite weak here. TVL has 5%, OFA base 14, and OFA 16. So they are much better, but they are still quite low. And we can see the training basic selector here does much better. We have 15% accurate coverage here, 23 here, and 30% here. So this is already much better, and we can answer much more questions for the same risk, acceptable risk. And yeah, I didn't say this is only in distribution, so the same distribution as the training effect, only VQA data. And now we can look at the result of our method, which is deep learning from your peers. And we see here that it's again improved compared to the selector, this metric here and all the other metrics as well. We have 18, 27, and 32, so around plus 3 or plus 4 points, plus 2 depending on the model. And it improved also coverage for higher risks and the AUC, as I said, which is the average metric. And so here is for the out of distribution, I chose to show only one specific metric, which I thought was very interesting, which is the threshold generalization, or we could say the risk generalization. And here we want a target risk level of 1%. And so we select a specific threshold on the validation set, which is in distribution for this 1% error. And what we show here is the test risk. So the risk on the testing set using the same threshold. And hopefully we would like the risk to stay at 1%, because once we say this is acceptable, we don't want the model to have 10% of errors. And we see here that this is not really the case. Most models become, and this is percentage of OD data. So the more OD data we have, the worse the model become at risk generalization. And surprisingly, the worst model is OFA large in blue, which was the strongest model, which has the biggest number of parameters and the biggest pre-training. And the weaker the models were, the better they are here. So this is the first surprising observation. And second observation is that compared to the baseline, which are dashed lines, our strategy improves for the 3 models quite significantly the risk generalization. And so to conclude this section, we propose the learning from your peers, which is the strategy to improve the training of the selector and is efficient in distribution and OOD. And as a perspective, first, I think it would be interesting to investigate this risk generalization and why models are so weak at generalizing the risk for out of distribution. And then also explore the reliability of very large multitask vision and language models for many other tasks. Okay, so to conclude this presentation, we explored the multiple aspects of shortcut learning and out of distribution evaluations. And we propose to reduce shortcut learning with loss functions and architectural priors. We propose the ways to detect multimodal shortcuts and have a better evaluation strategies, and also how to improve the reliability of VQA models. So to give a few perspectives on this work and on, I think, future works which would be interesting. So now in deep learning, the successful models are very large multitask models. So we can think of large language models such as GPT-3, 4, and that are now becoming also a vision language. And I think it would be very interesting to study the bias in them, because that training data obviously have some kind of shortcuts or biases that would need to be addressed, and especially if we think of the next generation VQA data sets like visual dialogue or vision and language navigation, which is about communicating with the robot who is moving in a physical space. This would be very, very useful. And as perspective for the VQA task, so we see that models are now trained on VQA, they beat human performance, and so this data set is not really useful as anymore as a training data set, but now models are using it as a zero-shot evaluation task. So they don't train on it and they just use it to evaluate their performance. And so GPT-4 has 77.2 zero-shot accuracy without seeing any of the training data. So that's very close to human accuracy, and that's very impressive. And finally, data and model efficiency. So to train those models, we need a huge data sets and huge models and big computing infrastructure. So it's, I think, a very important area to improve the efficiency. And finally, the last perspective would be human interaction. So VQA is a task that is not, we cannot use it directly for humans, and how to make those models very useful for humans would be a very important perspective as well. So thank you.
Thank you, Corentin, for your presentation. A nice presentation in time. So now we will switch to the question and answer section. So we will start traditionally with the viewers. And so traditionally we start with the furthest viewer. So as Elisa is remotely attending the response, I propose to start with you. So Elisa, whenever you are ready, the floor is yours.
Okay, thank you, Mr. President. Yeah, I guess Christian is probably further than me usually, but it's okay. So first of all, congratulations for this presentation and this very nice work. I thank you and your supervisor for inviting me to this jury, because I learned a lot. It was very interesting. The document was very pleasant to read. And I thought that the presentation was also very pleasant to watch. Do you hear me well? It's okay?
Yes, very well.
Very well. Too well.
What do you mean, Matthew? I should shut up?
Exactly, not exactly.
It's very strong.
It's a little bit strong here, but it's not your fault. It's not your fault.
Okay. Okay. Sorry.
It's okay. It's okay.
So I did ask a few questions in my report. Is it better now? Yeah.
Fantastic,
Yes.
fantastic.
I'm also talking a bit less loudly, maybe. And actually, I got other questions, other ideas, other things that intrigued me during your presentation. So I think I will. It will be a bit less structured, but I will still ask them. So I will try to do it in the chronological order. So about your first part about reducing shortcut learning. So this time you spent a bit of time explaining Ruby and then a little bit of time at the end explaining your special counting network. And so I did ask this question in my report, and so how do you combine those two things? Is it possible to combine them? Can you leverage the loss that you have, the fact that you're using the question only model in the first part? Can you somehow using also in this part in some way?
So you mean using a strategy like Ruby here? Could we use this to help reduce the shortcuts?
Yes.
So yeah, it should work, and we tried Ruby on an existing network, which is RCN, which is a classification network, and it did improve the results for some kind of distribution shift. So I think that it works well when the distribution shift is a condition on the question. So when given the question word, you have a shift in the answer distribution. But when you have a shift which is not this one, then Ruby doesn't work so well. And this is why in this work we evaluate two kinds of distribution shifts: the question condition shift and the more general distribution shift. And so yeah, Ruby would help in the first case, but for this network, it's a bit complex because this network is trained as a regression model. It's a regression loss which tries directly to predict the score. And so we cannot directly apply Ruby on a regression model, but we could think of adapting it and maybe merging before the output in the fusion before the fusion layers, maybe of merging two branches this way, but it's not as simple as we could as for a classification model.
So because, so for example, if I'm thinking at the same time as you're talking, so maybe this is going nowhere. So let's say that, for example, so here you have the same kind of biases. Like if you know how many zebras, for example, the most common answer is 2. You said it. And so this is really biased on the textual information, and this is something that Ruby should be able to somehow mitigate.
Yes.
And so I don't really see when you answer, you say, okay, the problem is it's a regression problem and not a classification one, so the tools cannot be the same. I'm not sure.
So I'm talking specifically about this model, the spatial counting network that we propose. This is trained as a regression model. So we have only one output, which is a number. We don't have multiple classes, but we could train it, and most of the other models train it as a classification problem. And they have 15 possible classes from 0 to 14, and then you have a score for every number. And then you can do this kind of merging of Ruby-like merging of the prediction of the question-only model and of the main model. But here in this case, since we have only one number as an output, we can't really merge. I mean, we could think of other strategies which might work. So maybe doing the average of the two predictions or some kind of merging of this information, but it would be a bit different from the original Ruby architecture.
Okay, and so about the shortcuts that you're actually tackling here. So it made me smile when I was reading the part about the spatial counting network in your document, because you say, okay, in Ruby, I tackled the unimodal biases, and with this one, I tackle all the rest. So,
Yes.
I think this was a bit strong. So did you actually check that the biases that you were tackling were so different?
Yeah, that's a good question. I have a slide here with the two data sets. It's very, but so yeah, we have two data sets. Basically, we have a data set which is very similar to VQACP, where we have in training and in testing different distributions depending on the specific object. So this is similar to VQACP. And the other one is odd even. So we have mostly odd examples in train and even in test. And what we mean here is that we consider that the shortcuts are like simple correlations between the input and one specific answer. So for example, a shortcut which will say how many zebras and the answer 2. And if we think of this maybe in an extreme way, where we have only odd examples in the training, even in the testing, then the shortcuts that are in the training set cannot be in the testing set, because you don't have the same answer. You the answer distribution is completely different, and so you cannot learn if you are using shortcuts from the training set. The shortcuts don't exist at all in the testing set, and maybe in this less extreme case, maybe here the most common answer for how many zebras is 3, because here we have mostly odd questions, and here it's going to be 2 because we have mostly even questions. So I think it's in this way that we said that we tackle all kinds of shortcuts, because we have such a strong distribution shift that is general on the answer distribution, that is not conditioned on the question, that a model which learns any shortcut here, this shortcut shouldn't really exist on the testing set. But obviously, we can think of more complex shortcuts, maybe that are still present in both sets. Like maybe if I ask how many zebras or how many horses are brown, actually I can just count the horses and give the answer. And this is a maybe more complex shortcut, which is not associated to one specific answer. And this might still exist in this sheet. So
yeah.
Okay.
Okay. It's because, well, yeah. And then I had a small problem when I was reading the document. It shows less in the presentation. Is at the end, I don't really know. So if I want to avoid shortcuts entirely, and have a good accuracy anyway. So we'll come back to that, because you just said in your conclusion that you don't need any liquid model anymore. But so what should I use?
I think first you should try to find the shortcuts that you have in your dataset, in maybe using some tools like this. If you have multimodal examples, or using some for image classification tasks, usually we can use attribution methods which tell you what part of the image was used in the answer. And we could also use them here for BQA, by the way. We didn't try this, but this could be an interesting experiment. And so first try to understand what kind of shortcuts you have. And this is after the release of the third BQA paper, people have been trying to understand this. And now we understand it a bit better. But so yeah, first understand this, and then how to reduce them. It's a very hard question, and depends a lot on what you find. And the most efficient way would be to collect new examples that don't have those shortcuts, that maybe are counter examples to those shortcuts. And this is what I think a lot of companies are doing. In real life, they try to find edge cases, and then they try to collect more data to that contain this edge case, so the model will be able to learn better. So yeah, this is the best strategy, and it's very costly, and that's why I mentioned here additive or generative models, maybe to create counter examples, and then we can add them to the training data, and this might help. This might help be more less reliant on the shortcuts, but obviously then we would need a different testing set, because if we use them to add training examples, we cannot use it as a testing set.
Okay. So to move on to this part, so the second part about the multimodal shortcuts. So first, one question to make sure that I remember well, and so this is only for the rules, the pattern sets that you're extracting are only you filter them to keep only the multimodal ones, right? So you don't keep the unimodal one.
No, here we kept all of them, and this is interesting. And I think in the paper we tried both approaches, and the results are present here are with only every shortcuts, all the textual and the multimodal shortcuts, and so this data set has multiple kind of shortcuts.
Okay, and what is the proportion of unimodal ones compared to multimodal ones then in your data sets when you extract the patterns?
That's a good question. I really don't remember, but I would say that they have I remember well there was a bit more multimodal shortcuts than textual shortcuts, but this is also it's very hard to evaluate because we have a lot of shortcuts which are very similar, but just like one word the difference. And since if we had the vision, the number of tokens grows a lot of possible tokens, and so like mathematically, then the number of very similar shortcuts will be much bigger for this case. So I think that there were more multimodal shortcuts, but I'm not sure if we count only unique shortcuts. For example, here, what sport and racket, we could also have what is sport and racket, or what sport field and racket, or something like this. So yeah, but I think there are more multimodal shortcuts in these data. Yeah, overall. Yeah.
Yeah, okay. So I mentioned it in my report also, but as a side project, I know that one cannot do everything during a PhD, and you did already a lot. But on this particular problem of pattern explosion, and there are things that could have been done to somehow reduce the number of similar patterns and redundancy in your answers automatically, but yeah, okay, so that's a kind of a side project. So in fact, my question was a bit, so I wonder when I was listening to you, if you, so again, I understand that one cannot do everything, huh? But did you go back and forth from your first part to your second part, or did you just, so what I mean is that, okay, now you have a method to detect shortcuts. And I was a bit frustrated because for this part, you don't actually propose a way to deal with them, but it's true that you do it in other parts. And I was wondering if somehow you found different or shortcuts that were not tackled in your other parts here. And you went back and you say, okay, now I'm going to try to use the method that I've developed before to deal with them. Did you do things like that or not at all?
Yes, I did. And specifically after this project, I tried a lot of different methods to try to reduce those shortcut learnings. So methods like Ruby, which I evaluate in this work. And also I tried a lot of methods which are based on domain generalization. So this is when you have two different training data sets which have different distribution. And here you can consider that the counterexample might be one distribution and the rest might be another distribution. And we might be able to use the domain generalization methods to improve, to learn a common to learn a VK model which is robust to shortcuts. And because I worked on another paper which does domain generalization for classification, image classification, and this is not included in this study, but I tried to apply it to this problem using the counterexamples here, and it didn't work at all. It didn't help reduce the shortcut learning. And yes, I tried other approaches inspired by Ruby. We can also think of applying Ruby. Also, instead of having only one question branch, to have a vision branch as well. Or maybe, this I didn't try, but would be interesting, maybe a shortcut only branch which uses those shortcuts. I don't know in which way, but maybe just a binary thing that there is a shortcut or not. Maybe this would also improve, yeah. And I tried something like this, but they were not included in the paper because none of them worked in the end.
Okay, well, that's very interesting. Actually, I was wondering why didn't you use a a visual only modality also in your first part. I forgot about that, but yeah, okay, so you did try.
We try.
Okay, and so there is also something that is a bit difficult, I think, on this part is that somehow so for the words you explain that you keep all the relevant words in the prompt, but for the images you have to decide the classes that you're going to detect with your object detectors. And
Yes.
and maybe you are missing the really important part for the system, something that maybe has no semantic for you or something like that.
Yes.
And this is a bit more difficult, I think.
Yes, that's correct. And here we use an object detection model which is pre-trained on the visual genome. So it's images very similar to Coco, which have a lot of different objects, and so I think the distribution is very close, and this is actually the same model that is used by most VQA models. Yeah, and we chose to use the same because we didn't want yeah, we wanted to use the same image representation so that the errors of VQA models will be the same errors here, and so that models are not penalized because of the wrong object detection, but really by the shortcut learning. But yeah, then this is also a completely different question. But so yeah, we use the pastoral trend of visual genome, which has, I think, many different, much more than Coco, for example, different objects. I think I don't know the number exactly, but a few hundred. Or, and also detects the attributes. So we didn't use the attributes here. But I think this is a bit missing because the attributes are also very important in VQA, like the colors or the texture or the size of the object. So yeah, I agree with you. It's a very difficult problem of what to keep here and what to keep there. And we only kept the objects which appear enough. Like if an object appears only once in the whole data set, we will discard it. But or should time that.
Okay. Well, thank you. And about the third part, so there is one thing that I think I misunderstood, or so I have the feeling that your selector at the end, the one that you're learning from your peers, it's a binary classification, right? It's correct or incorrect?
So it's trained as a yeah, it's trained as binary classification in that case. So it gives the score between 0 and 1, and yeah, but it's
but so at the beginning you said that what you're aiming at is an answer and a confidence
yes.
level. And so do you get a confidence level? I was not sure at the end.
So yes, here it's binary classification, but it's still a probabilistic model which gives a score between 0 and 1, and the labels that we train it with are 0 or 1. And actually, in VQA, it's not only 0 and 1. You can be like partially right. So you can have here the correct. It's a bit wrong here what I wrote. It's not correct or incorrect. It's either 0.0 or 0.3, 0.6, 0.9 or 1. We have multiple correctness levels, and I simplified it a bit here, but it depends on the number of annotators who answer the same as the model. And if only one annotator has the same answer, then you will get only 0.3 as the correctness score. And this is what we train the selector on, and not a binary classification. So maybe it's more similar to a regression than we train it with a quantum entropy loss on those targets, but it's a bit similar to a regression method. And using this approach, we have a confidence between 0 and 1.
Okay, I see. Okay, a bit more open or general question. So at the beginning of your document, you make the link between shortcut learning or identification and explanation. And so I was thinking about what could be the real link between all those things, and I was wondering. So for example, in your document, you give the famous husky example from Lyme, and where you say, okay, here typically the explanation algorithm has identified a shortcut learned by the model, which is the fact that it's relying on the snow and not on the husky features to take the decision, the neural network. And I was wondering, so if you look just at the feature attribution methods, isn't whenever you find an explanation and it's not related to what you're expecting, it's not related to your expectation, isn't it always a shortcut? I mean, there's a so can you use is shortcut learning a way to directly give explanation about things that are not expected, or do you see what I mean? I was really wondering what is the link, and if you can go from one field to the other.
Yeah. Okay, I see what you mean. Yes, I think they are very closely related, and I agree with you that if you see a correlation between some part of the image and the answer that you think is surprising and shouldn't be used for the answer, then it's definitely a shortcut. But also a shortcut, I think, is a bit different because it's maybe on more of a data set level. It's like a correlation that holds across the whole data set, and attribution methods only look at single examples. So I would say maybe that's the difference. And I would say we could use some methods like sorry, the method I proposed to detect shortcuts. You could use it after maybe an attribution method that will extract some part of the image. Maybe we would need to label those parts also, saying here is snow, here is the wolf, and then using a rule mining or a similar approach to find those shortcuts that will hold across the whole data set. And maybe they are not shortcuts because, as you said, if the correct region, if you want to detect a dog and the model selects the dog, then that's not a shortcut. But if it selects the grass next to the dog, then that's a shortcut. Okay. Here you need some kind of human, you need a human to look at the results and say, this is a shortcut, this is not a shortcut. And you cannot do it automatically, I think. Whereas in VQA, yeah, what we did was we thought that those very simple rules are kind of too simple for the VQA task, and then they should never really be completely correct, and we consider them as always shortcuts. But also, since we only look at the counterexamples, then the rules that don't have any counterexamples, which might be actually causal rules and not shortcuts, they don't have an impact on the benchmark. So that's less of an issue for us. But yeah, that's maybe what I would say between the link between shortcuts and attribution and method or interpretability.
Yeah, maybe. Okay. And my last remark, it's not really a question. So I think what you're doing is much more general than, well, it could be used in a much more general setting than VQA. So I was mentioning in my report, for example, multispectral analysis of outdoor scenes or stuff like that, because the fact, so the same way that somehow you want to detect biases such as the snow and the husky, which are in fact shortcuts, This is true for every model, because this is going to prevent a good generalization of the model on out of distribution samples. And so yeah, so I think what you did could be usable for much larger settings, and so I will try to use it in the future. So yeah, I just wanted to congratulate you again for this.
Thank you. Yeah, and tell me if it works well in the future.
Yeah. Do you expect it not to work well?
I hope, but you never know.
Okay, Mr. President, I leave the floor.
Okay, thank you, Elisa. So now we will give the floor to the second reviewer, so Christian.
Thank you, Mr. President. Thank you for this nice presentation. I really liked it a lot, as I did the manuscript as a second report. The manuscript was really well written. I enjoyed it a lot. The same way the presentation is really good. I even saw there was a banana inside. I heard it is mandatory here at the one in particular, but really
Yes.
is this? Thank you, Mathieu, for the invitation. I have followed the PhD a little bit because, as you know, we had a PhD on the same subject. We even shared the first name.
Yes.
So, yeah. What I go a little bit more into detail about what I liked. So what I really enjoyed in this manuscript presentation is not only the scientific work we did, but also the evaluation, which was really convincing. Lots of ablations, different tests, some contributions like Ruby. You made sure that it's evaluated not only on one architecture, but on cross architectures. You introduce new data sets, you open source your code, so all of this is on top of the scientific work we did, which is really good.
Thank you.
So yes, I have a couple of questions. The first one on chapter 3. So I asked a couple of questions which I also put actually into my report. So Ruby, I did a remark in my report, and which is more like a question. I have a suspicion. You mentioned that the method is doing bias reduction, and bias is kind of the counterexample to, well, it's to reasoning. At least that's what you claim, right? And that's what we also did in my group recently. But while reasoning can be defined as not using biases, reducing biases does not necessarily mean that you reason well. And this is exactly the question I have. Do you think does Ruby only reduce biases, or does it also lead to better reasoning?
Okay. Yeah, that's an interesting question. So I would say, if you are not using any shortcut or bias, but you're still getting the correct answer, I don't know what's exactly the alternative to reasoning. But yeah, maybe there is a kind of a middle between those 2 points. And yeah, I think the main impact of Ruby is to help, is to force the model to look at the image and to use the image in its prediction, and yeah, not rely only on the question. So like be further away from the question only model. So yeah, that's the main impact of Ruby. And so whether this helps reasoning or helps maybe to learn more multimodal shortcuts, maybe that's Ruby helps, and this might be the case that it helps partly at the reasoning, but partly at learning some multimodal shortcuts, which I showed in the second section, and which Ruby doesn't work on. So maybe that's a reason. So yeah, I cannot really say if Ruby helped only for reducing for learning reasoning. I think it might be a bit of both. Yeah.
Okay. On this chapter, I have a second question, which is on the fact that you are in 2 different regimes, whether you train or whether you test. So during training, you have this additional language branch, which masks on the loss, well, masks, not the loss, but has an effect on the loss. And then you remove it during testing. And the question is, what is the effect of this? I mean, do you have the positive effect on the gradients, which you described really well in the manuscript? And I really enjoyed this, and this is really convincing. But the fact that you remove this during training so that you do something else, you're not out of distribution in some sense with respect to training, right? Yes. What is the effect of it?
So yeah, first maybe I could talk about the effect of keeping this branch in testing. I think if we keep this branch in testing, and I tried it actually, then we have basically the same model as the first one. It learns exactly the same correlation. It has a very close scores to the first one. Like yeah, if we use this loss directly, this prediction testing, and this seems expected because yeah, this loss is learned on the same data set as this first, and so this should have the same correlation and using the same shortcuts as the main model. And so removing it, this is what helps. And so using this as a prediction, removes some image masking, so some will kind of decrease the scores of the classes that it will decrease the score of the classes predicted by this branch, because this will influence the predictions for some classes, and if we remove it, then we decrease the scores for those predictions, and so it's kind of a reverse effect, and this is what I believe helps the model to be less biased to ask the question in testing.
Okay, so there is no my question. I don't have an answer on that. Is there only a positive effect of this shift, or can there be negative one as well? And I'm not sure. I don't propose anything. I'm asking the question. The fact that you're out of distribution has obviously the effect you described, but also can there be cases where this is a problem?
Yes, it's a problem if you do it in distribution, then the score decreases a bit. That's I would say the first issue, but it's not a huge issue. The score doesn't decrease a lot, and then also maybe this architecture works well for the specific VQACP shift, but maybe it could be too strong for if we have a smaller distribution shift, or maybe too light if we have a stronger shift. And we didn't really evaluate like having different shifts in distribution and how we can adapt maybe this for different kind of distributions, or how well does it adapt by itself, because there is nothing really like specific components that we tune here, but the learning rate and all the parameters might have an impact on how much and maybe the weights of the two losses here might have an impact on how well it generalizes to a new distribution. So I would say maybe this aspect of the different shifts in distribution, and this architecture might not work for all of them, and this would be I think we need to evaluate this.
Okay. Thank you. I have a couple of questions to chapter 4, which certainly I didn't, for time reasons, present a lot here, but I'd still ask a couple of questions on them.
Yes.
And what I found really interesting is that you changed from classification to regression, and Elisa also asked a couple of questions on that. And what was surprising for me is that I have the impression there is a huge body of literature currently which replaces actually regression for classification currently. And I understand your motivation, and I think the zero-shot performance, which you mentioned at the end of this chapter, comes from regression, right? I mean, if you don't have class percent at all and you do classification, it can't work in regression. Since you have a continuity loss, naturally you have zero-shot performance. But this can actually also deal with regression by changing the loss, going from cross entropy to the smoothing losses, which have been introduced for age estimation, or there is even a whole class of literature is called ordinal regression. I don't know if you heard about that.
No, I don't think so.
Where you actually perform, technically speaking, classification, but the answers from the class predictions are generated with mathematical function, which ensures monotonicity and regression.
Yeah.
So basically, you do at the end of the day regression, but through intermediate classification, which works really well.
Okay.
So, yeah, that's basically there is no question. I don't know.
Yeah, and maybe I can comment a bit.
Yeah,
on
my
this.
question is what is your
Yeah.
feedback on this regression versus
Yeah.
classification? Because you kind of counter examples. In your case, regression works so much better. So how do you live with what's your opinion on this?
Yeah, and I think the reason was exactly this. We introduced regression because we would expect it to be less, to have less of a tendency to learn directly shortcuts from one input to one class, like classification models are doing. And then they will be able, and also it gives a structure to the output, and then you are able to answer in a zero-shot way or in classes that were very sparse in the training set. So that was very interesting to us. And also maybe something I add, and like Brad, is that there is a regression loss, but there is also an entropy loss here, which forces so this score here is just the sum of all the scores for all the objects detected. And there is an entropy loss here, which forces this scores to be either close to 0 or close to 1. And this also is extremely important for zero shot. And if we don't have this entropy loss here, then the scores are very close to the classification model, even with the regression loss. Regression is still a bit better, but not as much as with this entropy loss. And if we don't have this entropy loss, but we see that all objects basically get kind of the same score, which sums to 3. And so the model seems to be learning to do classification even with the regression loss by outputting kind of fuzzy scores here. And so yeah, regression alone was not enough to be completely robust to this, but with those two losses together, this is really what made the difference.
Okay. A small detail, but just from curiosity. So since you have this inductive bias, and I like this line of work a lot, so trying to find out what kind of algorithms you actually want to represent and forcing your network to actually be able to represent that. So that's pretty good. Just a small detail, the fact that you have a single attention head in the transformer, is this a design choice because you want your transformer to do counting and you want it to do that in a single head? Was it motivated by this, or is it just one because you have like
let me think, I try to remember. So first, yeah, the goal of the self-attention module for us was to do some kind of non-maximal suppression, or like remove objects which would be close or the same object but counted twice. So that was the goal for us of this network. Why only one layer? I think this came from ablation and maybe efficiency.
Okay.
So yeah, I don't think there is a specific reason for this, but I don't remember.
Okay. So I think this was in the same chapter. I noted it for chapter 4, but it's not related to classification. It's more related to the data set. I might confuse chapters. No, I don't, I think. So you have introduced these new data sets, and my question is on the shifts which you introduced or not actually. And so there's a difference between what you did with your data set and the data set we did in our group. And there is no, I don't compare them qualitatively, but I'm just asking this question on whether this shift between training and validation is necessary, right? Because we all agree, and that's what you said in your manuscript, that we need a shift between training and test.
Yes.
This is what we actually want to test.
Yes.
But now, if you have a shift, which we in our group we introduced, then you can actually, and the shift must be different from the shift we do between training and test. Obviously, there must be two different shifts. If you do that, then you can actually maximize output distribution through through checkpointing. Whereas if you don't, like you do, you're forced, or you can and should do that by actually design choices.
Yes.
So what's your take?
Yeah, that's a very good question. I think no one really agrees completely on this, but there are some benchmarks which have like a domain bed, for example, has the two different, I think, setups. So one you have a validation which is in distribution, and one you have validation which is out of distribution. And so yeah, it's a very good question, and I think the first chapter. So I mean, Ruby. The problem with the data set is that it has no validation set, and everyone is evaluating on the test set and doing the hyperparameter tuning in the test set. So I think this is one of the main flaws of KCP, and I think most of you agree here. But and so yeah, in this benchmark, we tried to have a validation which was in distribution, and so yeah, it has benefits of yeah, not being specific to one out of distribution then, but it has also the drawback that usually the best method, if you have a validation set which is in distribution, is the original method, and if you try to add some new losses or even new architectural choices, it will make your validation worse. So then you still need to sometimes test on the testing set. So yeah, it's a very hard question, and yeah, I would say you test architectural choices and you allow yourself to test them on the testing set, but not tune the parameters on this testing set to remove a bit of overfitting, and that's what we chose to do. Like tune all the parameters and all everything on the val set, which is in distribution, and test the architecture on the test set. But yeah, I agree that maybe it's better to have a known out of distribution, which is different from the testing set, and yeah, but I mean, I don't think there is a better answer here, and just two different choices, but yeah.
Yeah, okay.
Yeah.
Thank you. So Elisa also already mentioned the image-only baseline, and I found that fascinating. I mentioned it in my report that the image-only model is actually quite good on your KCP. And I don't have the table.
I might have the table somewhere. Yes.
So what does that actually mean, right? I mean, we all naturally expect question on the biases, obviously, how many bananas are in there too.
Yeah.
But image only in counting in particular, that kind of means that the model seems to infer what is the object we actually count here, just looking at the image. Right?
Yeah. Yeah, it's a good question. So yeah, maybe so yeah, let me try to remind a bit. So yeah, Tally QACP, we have this sheet in distribution. Yeah, so maybe the reason comes. So this guy is actually very close to the random here scores distribution train. And this is so this car is actually not so good because it's basically the same as if you look at a random prediction that follows the distribution of the answer. And so this means that basically this image only might be saying 2, it only says 2, for example. And I think this is very close to saying always 2. But it's much better than the question only, because the question only will learn an inverse correlation between the object and the answer, and this model will be completely fooled when we see the distribution. But actually, the overall answer distribution stays quite similar between the two. The training and the testing have very similar distribution overall, but very different condition distribution. And this is why this model gets fooled, but this one just learn the overall distribution because it doesn't have access to this bias. So yeah, so that's the reason. Yeah.
Okay, I didn't see that. Okay, that makes sense. Okay, thank you. I have 2 more questions, one for chapter 5 and one for chapter 6. Chapter 5, I will not ask too many questions because I actually counted on Elisa. She must have been really happy to see this thesis on using lots of pattern mining actually. which really comes from. I have one question. How can you push this further? I mean, for the moment you have patterns which are now multimodal, which are now much more interesting than unimodal than before. But how can you go forward? Because your patterns are bags of words, right?
Yes.
Can you include spatial relationships? Can you model an area? And where do you stop? And this is and this goes in the direction of what Elisa said. So when does your shortcut then become proper reasoning? But what I think personally, I think there is no answer to this question. But what do you think? How far you can go?
Yeah, that's a good question. We discussed it a lot with the co-authors when we wrote the paper, and yeah, here it's the most simple we could have is just the occurrence of a word. We don't even know if this word appears multiple times or not. Just if it appears once or not, or multiple times. And we thought that this was reasonable to say this is a shortcut. And we thought of adding things like negative words. So if a word is not appearing, then can it be used as a shortcut? And I think it can be used as a shortcut. But the problem is that negative words are, this might be related to what Elisa was saying of explosion. You have thousands more negative words than positive words, for a given example. So it's very hard to include them without your algorithm going completely out of memory. So we tried negative words, but well, it was very hard. And yeah, and I agree, if we go too far, then we end up with a big day model, which we hope will learn reasoning. And in the middle ground, we thought of adding maybe not only occurrence, but maybe how many times the word was present in the input. And also maybe we thought was important was the positions of the first few words. For example, what sport is, because here the words are not ordered, just a bag of words, as you said. But we thought that the first 2 or 3 words might be very important to know at least the kind of answer that we expect. And we tried also to add this as an input feature, like specific for the first 3 words. But it didn't really help a lot to find the shortcuts. We didn't include it, and we kept the most simple thing. And yeah, I agree. And I would have liked to add the attributes as well of objects, and because the colors are often used in VQA. But then if you add a color, you need to refer to the object. And this is hard because then you have, if you need to have tokens for one object that has one color, then you have this explosion again of tokens. And so, yeah, I would say the main problem to, if we want to add more complex thing, is the number of tokens that explode very quickly. But yeah, maybe with some determiners, as Elisa was saying, we could tackle this and add some more complex tokens. Maybe spatial reasoning also. This is also a very important VQA ability, asking is this object on the left, on the right, top or down of the image. And we didn't try this, but I would expect that this is this still a shortcut? So yeah, the negative one is interesting because there are obvious cases of a negative which is not a shortcut. If you ask, is there a cat, and you have the not cat token, then I would say this is a proper reasoning rule, and it's not a shortcut. If you know you don't have a cat, and the question is there a cat, then this is not a shortcut anymore. It's a proper reasoning rule. So, yeah.
Okay.
Yeah, it's a complex question, but we try to improve a bit and
okay. I have one last one. I actually asked the question in my research on my first one to know whether you agree. It's in chapter 6, where you presented the method. I forgot its name.
learning from your peers.
Yes, exactly. And so one of the main differences is that one of the competing methods did a single split And you change the splits here and you motivated that by better data usage. And I actually, I'm suspicious and I think the real effect comes from doing something else. I explained it in my report, and basically if you do a single split, then you need to find out whether the model is correct or not. And you have multiple ways how to learn that. You can learn the decision frontier in the reasoning space, or you can approximate this by learning frontier in input space to the model. So you find out which are the properties in input space which define correct reasoning. And by turning the splits around, these frontiers in input space are not variable, they shift all the time, and you need to learn the split in reasoning space. Do you agree with that?
Yeah, I read the report and I thought it was very interesting. And this, I think, yeah, is related to maybe under specification. So that your model has many ways of answering the question. And if you have only one model, then yes, the selector will learn exactly the decision function of this model, which might be shortcuts. And then the G will learn the shortcuts. I completely agree. And if you have multiple models, then yeah, I think you might be right that they all will learn. They are all the VQA might be underspecified, and as you said, multiple solutions are possible. So they might all learn different solutions, and then if the G has to learn more general thing and not adapting to every VQA model and learning the specific shortcut that each one of them learn. So yeah, I would say this is a bit similar to ensembling. It works for a similar reason that if you have under specification, all your models will learn a different solution, and when you have read them, then they are much more robust to all kind of also OD and so.
I'm not sure that ensembling does the same thing here. But again, I mean,
yeah. Yes,
I think it goes
different, but
beyond or something. What I found interesting here is that you can see this actually as shortcut avoiding, right?
Okay.
So you did some kind of meta shortcut learning. So your selector was prone to shortcuts in the original solution, and you removed one of the shortcuts.
Okay.
Basically learning on input space to the VQA model. It now needs to learn on the model space, the VQA model.
Yeah. Okay, I see. And maybe this is why it was better for OD as well.
Yeah. Okay. I don't have any questions anymore. Thank you. Very much. And back to you, Mr. Oliver.
So thank you, Christian. So now we will switch to the examiners. So when checking who is further, we actually noticed that Dancette is actually further than Marconi, but as Marcus is attending from the US, I propose to give the floor to Marcus.
Yes. Yes, thank you. Yeah, I'm still, yes, I'll start from Dancette soon, September. Yes, thanks for inviting me. Thanks for giving me the work, Mr. President. And thanks for this nice thesis, Corentin, and this nice presentation. Maybe I start with a question. In your thesis, you mentioned modular models as one version of VQA models, and I think you haven't really examined them so much in your thesis. But wouldn't they solve lots of the problems you tried to address, at least theoretically, and maybe you can also tell me why they don't solve them, including generalization to different tasks, or like handling bias, or also handling maybe generalization to out of domain, because they're just modular, so they can handle all these problematic or challenging cases.
So you are talking about modular models, like neural model network.
Yeah, that would be like sort of one example. I don't want to like restrict it to this specific instantiation, but I mean, if you think of different ones, that's also fine. But we can also discuss this specific one, of course.
Okay. Yeah, obviously, I think they work very well for this kind of shortcuts, and they work very well for specifically data sets which are a bit maybe more constrained, like Clever, the synthetic data set, where you know exactly what operations you will need, and then what and then you can construct the modules specifically for the task that we're trying to address. In my opinion, in VQA, they seem to, the task is so wide and has so many different abilities that it's very hard to define very specifically the modules to achieve the one specific goal. And so, yeah, a lot of us have been doing this. I've been trying to do this, but you still have a lot of learning going on in all the modules, I think. And I don't think there is a model which works very well on VQA, where the models are all like predefined and don't learn anything. And you just have some maybe switching between switching function which is learned. You also need some learning inside the individual modules. And I think this is where the problem of biases and shortcuts might also appear in your modules. That they might learn some shortcuts and they might be as biased as a non-modular neural network. And yeah, I'm a bit less familiar with the performance of those models on VQACP. But yeah, I know that they work very well on Clever, and also Clever, where there is a distribution shift, they also work very well. Yeah, but since I'm a bit less familiar,
Okay, so sounds good. Thank you. In my understanding, your thesis, you mainly looked at images and text. How does your work apply in cases where you have sort of extending all these domains, videos, maybe robotic actions, or on the textual side, dialogue?
Yeah.
Do you think sort of lots of your models could apply there, or could some of those modalities help, or could they make things more difficult? Can you sort of discuss that a bit more?
Yeah, yeah, I think they all could be applied to a lot of different tasks. Those three architectures, maybe the chapter I didn't present about the counting a bit less, because it's very focused on counting and it's an architecture for counting, but the rest of the thesis I think is very general and could be applied to other work. So video, I think would just be a small shift from image. I mean, the architectures are a bit different, but maybe the biases are very similar. And then, for example, video QA, I know some people have tried Ruby for video QA tasks. I had discussions with some people working on video QA. So video QA is questions about videos, and some people have tried to use Ruby or other architectures like Ruby for this task. So yeah, so it works and it has been tried. Then the two other models, the last one, reliability, is also very general and has nothing specific to VQA. So this could be applied in, I think, any task. And then the detection of shortcuts. This is maybe the most tricky one, because for each task we need to define what will be your tokens. And for robotics, for example, it's a bit less clear what is a token, and is it like one movement, or yeah, I'm less familiar with the robotics. But yeah, if you can define some input tokens and you believe they might be used and they might correlate to some output, then yeah, I think everything could be used for many of the tasks. Yeah.
And do you see that any of those things helps sort of having like a temporal modality or having a dialogue helps with any of the sort of problems you try to address? Sort of this, basically the shortcut learning can sort of help this sort of more than just, I mean, sort of an image and a single questions are very, I mean, they're sort of a very static single input. But if you have sort of more input, both on the language side or on the visual side,
Okay.
Do you see that this could help with the shortcuts or make it worse? I mean, yeah. And if so,
I think having more inputs makes you even more vulnerable to shortcuts, in my opinion. And for when you have a whole dialogue, then it's a bit more similar to the question answering task, maybe where you have a context. And we also know that it's subject to biases and shortcuts. And for the video aspect, yeah, I don't know exactly how it would affect the. I know that most of the tasks that work on video, usually they use very short videos for a few seconds, which are very static also. Maybe only one action is happening, and you could summarize it in 2 or 3 images, and that's actually how people usually implement the models. Is only subsample 3 or 4 frames, which then I think is much closer to an image task. So yeah, but yeah, it's a good question. But yeah, and I read some papers on video QA, which was also subject to similar kind of shortcuts. So I would say, yeah, it's a very similar problem.
Yeah, I definitely agree. I think especially the existing data out that's in the literature with video are very limited in many aspects. Do you think sort of in an ideal case, there could be something done in a sense sort of, I mean, more sort of what humans have available, sort of unrestricted video, or like even sort of being able to examine an object that sort of, like I said, sort of some actions from a different perspective could help with some of those things. Or like, I mean, a robot which sort of has the ability to ask another question, take a different perspective.
Yeah. Yeah, that's a good question. I think if you have the ability to take an action and change your perspective, this might help with shortcuts. It might be easier to learn a causal model of what exactly matters and what is just a background or. But yeah, if you can, yeah, act and then get some real feedback from the action you took. But this is very hard to do in the real life, and if you have longer videos, even longer videos, I would say are subject to the main problem of shortcuts, since they are still a static data set and static data sets. I would say it's the same problem.
Okay, yeah, makes sense. Maybe sort of, do you see a way to give those models or any of those models you have like feedback in the sense of what you identified sort of, okay, now as a human, I identified this model has some kind of shortcut, like that. No, I'm missing an example. I mean, maybe they associate bananas with yellow, and sort of, okay, you could start maybe telling them, all bananas can also have different colors. Do you see this sort of a way that you can give feedback to a model that it then incorporates? So in a future answering, it won't be so biased to this specific thing. Sort of that you can sort of the model can sort of you can give it feedback and it can learn and evolve. Similar that if you have like a child or something, you can sort of continually learn.
Okay. Yeah, that's a good question. Yeah, if we think of simple VK models, yeah, we could incorporate short feedback in new data and just train with it, but this requires a lot of data, obviously. And yeah, I'm thinking of maybe with the new very large language vision and language models, this feedback might be easier to actually use. Most of them are trained with human feedback to improve their after the pre-training. They do some human feedback. They train them on human feedback to align them closer to what the human is actually expecting. And we can also think of maybe just adding them to some kind of prompting. So the feedback that the human gave over the previous conversations with the same user. The user gave some feedback, and this is kept in memory and used as a prompt to initialize the model and give a better context, and then models might be able to better answer. Yeah, I would expect this to work. But for this specific VQA architectures, yeah, I think you need to then add new data and refine. They don't really have this in-context learning ability. So, yeah.
Okay. So maybe next question is just more to the last work on reliability. I think at this point you have this single threshold to specify a risk. So how would it work if you would like to have? I mean, clearly you can imagine that there's sort of a risk for certain things, like sort of different questions or different tasks you might be interested in different risks. For example, crossing the street, you want to be really sure you get it right, but recognizing some other aspects, you might be sort of less interested, or you might want rather higher coverage. Yeah.
Okay.
How do you think about that?
Okay. Yeah, that's interesting. Yeah, maybe a secondary question is, can we expect the model to do it by itself, of adapting the threshold based on the severity or the dangerousness of the situation? And I would expect those same, like those specialized VQA models. Of course, they cannot do this task. They have no outside knowledge of VQA. They don't know if a task is difficult, is dangerous, or if it's safe. So then if we use these models, we will need to kind of define for every application what is the acceptable risk. And maybe if it's in a car, then you want a very conservative risk. And if it's in a home, maybe it's acceptable to have slightly higher risk, because you have less possibility of a danger. Maybe with a child, it's very dangerous in the home, but yeah, but maybe and similarly with those more recent models, which are trained on very big data sets, they have this kind of knowledge of what is dangerous and what is safe for humans, even if that may be very superficial, and I'm not sure it's yet ready, and then we can trust them on this, but they might have this clue of what is dangerous, and then we could use them and ask them about is this a serious question, and does it need a very conservative risk, or is this harmful or harmless question? So I would hope that the models in the future have this knowledge of the world and know what's a difficult situation.
Yeah, that makes sense. And then you mentioned, I think sort of this maybe relates sort of to this you mentioned like on your last slide that GPT-4 had already very high performance, zero shot performance. Do you have any idea how good it is, or sort of good in these challenges you mentioned today with respect to distribution shift, and also with respect to risk and estimating reliability?
Yeah, that's a good question. I would expect them. I would expect it to have a very good calibration in a zero-shot manner, like to know if it's likely to be correct or incorrect. And there have been some papers on the large language models. We know that if they are not fine-tuned on a specific task, they have a very good estimation of what they know. But as soon as we fine-tune them, then they kind of lose this ability, and they become very overconfident on this task. So yeah, I would really like to try GPT-4 on VQA and be able to estimate its confidence about its answer. And I would expect it to work much better than the previous models, especially in this zero-shot accuracy setting.
Makes sense. And maybe my last question, so how do you think is it those observations you have in your thesis for models, how is it different from human bias and reliability? And can we either learn from humans, or given these larger models, should we learn from those models?
So I mean, how humans differ compared to models in the reliability metrics and
Yes.
Yeah, I think humans are much better at this, at estimating what they know for this kind of questions. Are they able to answer a question about an image? Everyone should be able to say, I can answer or I can't answer based on the image, if it doesn't require outside knowledge or something like this. But then, yeah, we know also humans do have biases and sometimes can be overconfident on some knowledge, actually, some belief or some knowledge that they have of some events but the world. Maybe in this aspect, humans are not so reliable, and maybe models are actually better at this. I'm really not sure, but yeah, I would expect for now humans to be better in all reliability metrics, but this might change soon.
Thank you for the answers. I think I'm done with my questions. Thanks. Giving back to the president.
Okay, thank you, Marcus. So now we'll switch to Dancette.
Thank you. Thank you, Corentin, for the presentation. We enjoyed it a lot. There was a lot of stuff I knew about, but nice to hear that all put together. So very nice presentation, very nice thesis. Enjoyed reading as well, good writing. Let me start with some questions about the learning from your peers chapter. So first, a basic question about the coverage risk curve. Is that the same thing as a traditional precision recall curve, just with another name, or is there
it's not exactly the same metric. So it's not the same metric. So precision, I think it's positive divided by. I actually remember, but they are different metrics. They don't give the same scores. And precision, gives you like how likely you are to get the correct answer. I think for an example that you selected, how likely is it to be correct? And recall is more like if you look at all the correct examples, how much of them do you retrieve? And so those are unrelated metrics. They don't have the same formula exactly. Coverage is not recall because it doesn't really care about true positive coverage. It's only the percentage of positive divided by all the examples. So there is no notion of true positive in coverage of correct or incorrect. Coverage is just how many examples did I retrieve. That's, I would say, the main difference. And the risk actually would be 1 minus precision, I think. I would say.
So the coverage is not the same as the recall.
No,
the risk is just 1 minus d.
I think that's right.
Then about the task itself, well, the setting itself, it sounds very similar to doing OD detection, where people have developed methods over the years where they basically come up with a score that they have to put a threshold on, and it's really about finding examples that are like beyond what the method is capable or the model is capable of handling. So I know there was a bit of literature review in which you included some of those methods, but I didn't quite get how this setting is different or maybe more difficult or not. I'm not sure.
That's here the goal is not to differentiate between OOD and in distribution, and that's, I would say, the main difference here is to differentiate between correct and incorrect. And there is a very high correlation between the two. And at VQA, for example, most examples are incorrect, and then they are very hard. And we would say that the model should maybe reject them all, and then the model should do OD detection, and so be able to reject them all. And that's a very interesting question, because that's actually the first approach we thought of also when we started this work. We started to learn the selector. So I go back to the architecture. Here, in addition to internal features, we try to add some OD detection model, which would also work on those internal features and would give an OD score, like you were saying, and fit this to the selective predictor. And we were hoping that this score would make the selective predictor better, and we'd be able to use this score to differentiate between the OD, which should have very low confidence, and the institution which have higher confidence. And yeah, and I spent maybe 2 or 3 months trying this, and in the end, nothing really worked. And I tried a lot of different OD detection methods, like fitting some distributions on the internal features, and then looking at the distance between the distributions, or some also non-parametric like KNN with the training data for the detection methods. And none of them really improved. So when you try to do this, the difficult thing is that you might need some OD data during training, because if you have only in distribution data, then the model will only see very high scores for the OD score. And so we try to train the selector with some known OD data, which is different from the testing OD data. And we used VisWiz and OKVQA, for example, as known OD, and tested on at VQA. And this didn't help at all the selector. And that was a bit surprising to us, because some other works actually do this. I think this work for NLP, they try, no, I don't think they try a OD score, but they tried non-OD, training the non-OD. But some other works do train with OD score as well. And for them, it worked well. And for us, it didn't work at all. And so we are still a bit unsure why is this. Maybe the OD are too different from each other, but then the scores have a different distribution, and then the selector is not able to learn them. So yeah, that's a possibility. Yeah. But yeah, it's very related. Yeah.
Yeah, thanks. Yeah, I can see that maybe there's different way of doing OD, like if you look at VisWiz or some other MITRE distribution chips.
Yeah,
that's very different.
Yeah, VisWiz, the images are completely different. At VQA, the images are the same, but the text is very different. So
yeah. And so the fact that the new method works better than the MaxProp baseline basically tells us that the softmax scores that are used in MaxProp are not correlated with the accuracy of the examples. Is that correct?
That the confidence score, you mean? Yeah, it's about the ranking. Yeah, exactly. Those metrics are metrics about ranking, and so yeah, it tells us that using the MaxProp are not correlated with the final score, that the rankings differ too much. And then this method improves the ranking of examples.
Yeah. So does that mean that we are maybe not training the base model with the right loss with this objective in mind? And would you see a way of maybe training the model so without the selector, but achieving the same objective basically, such that the score of the softmax is directly what we hope it will be?
So yeah, it's possible, and so I would say the obvious answer is to do some calibration of the logits, so that the probability of the answer is actually the probability that the model is correct. And they tried this in this paper, which proposed this method for VQA. They also compared it to calibration. So you have this additional loss, which is BCE loss, I think, or I don't remember exactly which loss, but it's after the training of the VQA model. Then you do a calibration training, And so, yeah, you have some calibrations don't change the ranking, so you have to choose the ones that do change the ranking.
Yeah,
And there are some
so
which,
it's a non-monotonic.
yes,
information
it's
as
a
well.
non-monotonic calibration, and this improves already a lot compared to MaxProb. But it's still the selector is still much better. And yes, maybe some other losses, not percentropy would be better. That's maybe force less the model to be very confident and close to one, and that's possible and to work.
Then just one more question to bounce off what Christian raised, which was very interesting. The fact that you train with this scheme where you will leave out some subsets like in multiple rounds. Those different subsets, are they sampled just at random?
Yes.
From the
Yes, they are completely random. And yeah, we thought it was very important because we want those models to have very close behavior and very close correctness and accuracy, so that this model can learn like that. Yeah, the can learn a single. So actually, we don't care that they are very close together, but we care that they are close to this model, so that the decisions. This is not completely out of distribution. So yes, we chose to have exactly same distribution. Yeah, there are sample randomly. Yeah.
Okay, so so I was going to ask, but you almost replied already. I was going to ask if you consider some other schemes for sampling the data, so making heterogeneous subsets of the data. So using maybe some sign information such that the models, well, different models actually do capture different shortcuts in the way that Christian maybe proposed. Could be one way to explain the.
And that's true, yeah, and yeah, as Christian was saying, maybe the way it works is more about learning to generalize. Maybe then it might make sense to have different training data or also different architectures here. I think one reviewer was asking also in the paper why we didn't use different architectures in the three models. We have diversity in them, and so yeah, we answered we don't want diversity here. We want that they are very close functions, but maybe it would help actually to have diversity and maybe training multiple models for each subset also, or with different parameters and assembling them. Or we think of many different things.
Yeah, I think if you had multiple subsets that were non-ID, then and you say you make those non-ID subsets in a clever way, in the sense that you inject some information, and it's very close to a domain generalization setting in which you try to find something that's kind of invariant across those subsets.
Yes, yeah, that's true. We could merge those two disciplines together and try to find the common function, common correctness function among all the models. That could be interesting to try.
Very good. Next question. Yeah, one more. That one too. Yeah. So one more question. Well, let's go to the future and what you think might be the future of this field. So you had some good reflections on the large scale pre-trained vision language models already. Do you still think or have experience about your appearance of shortcuts in those models? Do they still capture something that we don't want from the data, even in the zero shot setting?
Yeah. So yeah, I think they might be better calibrated, so that I think is true, and their output probability will be closer to the probability that they are correct. But this they learn shortcuts. I think they still do, and I think that's why most of them are not trained in a single step, only pre-training, but then they do fine-tuning of human annotations and of preferences, and then reinforcement learning. So there's all those multiple steps to try to align them to what we want them to say, and because they have a lot of biases that come from the real world, that might be sexist or racist, or so this is a bit further away from this thesis, but I didn't really talk about those kind of biases, but they are trained on a lot of different data where we don't really control the source. We don't know what are the biases of the data. So I believe that they have a lot of biases, and that's very important to control this and make sure they are safe to use. And
Then what will be the next step? Do we think we can use like the existing data sets? Are they still relevant for discount models, or do we need to measure something else or in some other ways?
Yeah, I think this specific data set as a training set and testing set is not really relevant anymore. And yeah, either, as I said, using it as a zero-shot evaluation, or maybe building some more complex and maybe closer to the application data set, like dialogues. And VisWiz would be an example of a data set very close to the application. And it hasn't been used a lot in the past few years because I think it was very hard for the models. It was really too hard for the previous models. But now it might be time to use it more for evaluating those very large models. Yes, and building more realistic data sets of dialogues. And I think there are a few already visual dialogues. But yeah, I expect more data sets to come that are better and closer to the application.
Very good, thanks.
Thank you.
Thank you, Damien. So now we are close to the end of the questions. So yeah, close to the end. So I will just take the opportunity to ask a few more questions before leaving the floor to your supervisor. So first, thank you, Corentin and Mathieu, for the invitation. So yeah, very interesting work. So first, I have a comment. I'm not a big fan of the terminology OOD in the case of shortcut learning, and I'm not sure that they are really synonymous, and that there is a one-to-one match between OOD and what you look for in shortcut detection. Okay. For example, in this chapter, I think that there might be something more related to behavior or aleatory uncertainty, more than technical uncertainty. It might be a bit misleading some okay, and so I will just finish by maybe a last question on this question about this large language model. So I have maybe two simple questions. The first thing is that you've been trained to detect and to try to mitigate some shortcuts in several ways. So when you have a large language model, that can be a huge variety of shortcuts that you can imagine. That are trained in a very large data set and tasks. So how would you handle this?
Yeah, I think I would handle it on application basis. So not trying to look in the whole model for shortcuts, because I think that's a very complex task, and more like look at one benchmark, one evaluation, or one application, and then those methods can be used in similar ways as with a large language model, because they just you have one task, input output, and you can try to find some shortcuts that the model is using, and try maybe to fine tune it to reduce its shortcuts then on this specific task with some fine tuning. That I think is possible, and I don't believe it's a problem that can be addressed generally in the model, saying we will remove all shortcuts and all biases, because that's not it doesn't really mean anything to remove all biases. The world has some biases, and they will be reflected in the model. So I would expect, that it's better to look at a task, look at the failures of this task. Are they due to some shortcuts? Maybe they are not due to shortcuts, they are due to just the difficulty of the task, and the model hasn't been trained on this data and cannot achieve it. But if they are due to some shortcuts, maybe we can reduce them for this task by fine-tuning the model. So yeah, we would use this approach.
And the last question, the way around, do you think large language model or multimodal model can be leveraged to reveal some shortcuts in state-of-the-art model? And how would you use them for that?
So we use a large language model to analyze another model.
Yeah.
Yeah, I think that's possible, and maybe yeah, we were talking in the beginning of the question with Elisa that if you have some attribution methods, for example, that will give us some correlation between some part of the image and the answer, then you need a human to look at this data and say there is a shortcut or not. And maybe those large language models might be able to do this task for us. You give them a subset of the data where the model is failing, and maybe some the model is correct, and with those attribution maps, and I would think that they are able to give you a textual summary of what is the shortcut in this data set, and then you can leverage. You might be able to collect more examples and maybe to summarize a bigger data set by giving it a lot of examples that it might be long for a human to look at all of them and annotate. I would expect that this would work. Yes, this is an example. Yeah.
Okay. Okay, thank you very much, Corentin. Congrats. I stuck with my question, and I think it's a floor. You're supervisor on that.
Yeah, thank you. Thank you very much. First, I would like to congratulate you for your very nice presentation of today. Yeah, it was very, perfect in time. And thank you. Yeah, very well. Of course. I would like also to say thank you to the jury. I mean, to all of you. Thank you for your time, for viewing, and thank you for coming today or being in this year today. I know that it's it's always time, and it takes time, and sometimes when we can have some problem also with personnel or other thing that makes the things tricky to do, and today it's perfect. Okay, so thanks everyone. So I just want to give a few words about the context of your PhD to come back to the yeah, it was I mean, like at the beginning when you just arrived, you were straight into the machine with this co-lead project with Caden and the Ruby project that very fastly, I mean, like converged to very nice publication, and so that was the beginning of your PhD, let's say. And that was also after this a time to think about okay, what is the next step, what we want to do on VQA now, more generally. I mean, like it was the beginning also of my chair, and so we were thinking together about what is beyond ImageNet, how to do zoning in deep, etc. So that was really, I mean, like this time to think about that. And so finally, it's great to see that you answer to that question by another question, or so, and going through the shortcut learning things at this detection or correction, and then depending on the different proposition that you have, but and this is the way that you answer to Christian to learn how to do. I mean, like really, I mean, like, or if you detect a shortcut, it's not, I mean, a straightforward way to do somehow reasoning, but as you say, if you remove all the shortcuts, I mean, the machine is obliged to reason, to answer to the question, because there is no shortcut possible. Okay, so, but okay, it's a specific way to answer, but okay, I really appreciate, I mean, like this, and I would say, and of course, I mean, on the other side, we try to do explicitly, I mean, like this kind of block reasoning into the deep, and this is the counting stuff that you presented. So we really, I mean, like try to do different things, and you, yeah, I think you have been very successful on these two sides, and also you have been able to go, I mean, like to an internship in Meta in California with Marcus, and that was also fantastic opportunity for you that time, and with a very successful also after collaboration with Marcus with this last CVPR paper that we are going to present in a few weeks in Vancouver. So it's fantastic for that, and I think yeah, really, I mean, like, yeah, you did fast, you did well, you work a lot, and so and also it was a pleasure to work with you and to have you in the team, because as I say, you are a very nice guy, and I think I don't know how to translate in English, but en français on dit t'es une crème. Yeah, very easy to work and good to have you in the team. So thank you for all of that, and also I have to say that there are many works that you did that you not presented. Neither in the document or in today, but I have to mention perhaps the Fisher collaboration, I mean, like that you have, that is also another way to think about environment and different contexts, and typically, I mean, like the kind of things about learning. And also, and this is for the learning part, and also for the architecture, you did a very nice work on the perceiver, so you try also to do some kind of efficient learning for perceiver, etc. And we publish it also in CVPR, and even some work that stay unpublished, and that was very interesting things about data, let's say data augmentation in VQA, and thinking about how to generate, I mean, like new sentences as a new question for the VQA task. And I think typically, I mean, like at that time, we didn't have good enough generative models, and in particular, large language model to do that. But for sure, today, if we reconsider this kind of task, it will be much more efficient for that. So just to finish, I think, yeah, as Elisa pointed out, you really, I mean, like, cover many different things that really go through general questions that we can have today. I mean, like about, of course, setting and yeah, shortcuts, and everything is much larger than VQA. I mean, like where we studied it, and certainly I think that today you are one of the worldwide experts in vision and language models, and so I think the moment where we have this kind of second revolution about the large language model and the crisis that is coming together with that, and I think it's important at the moment to have to really think about what we are going to do and how we can talk about that, and we need experts to talk about what's happening today. And so I think I really encourage you to think about that also by choosing the way that you are going to. I know that you are passing a lot of interviews, and I encourage you to choose the right solution. I mean, the solution to do AI for good. Yeah, thank you. Thank you.
Thank you, Mathieu. So this ends the defense, and the defense. Now we have the deliberation. So I don't know if we stay here.
Yeah, because of the connection.
As the